Hello everyone, welcome to the second video in Chapter 8. We're going to be talking about geometric distributions. Hopefully you have your notes in front of you and you're ready to start writing some things down. So here we go. So here's the scenario. In a large fish tank, 30% of the goldfish are males. A customer desires a male goldfish. So a store employee scoops into the water and he captures one fish. If the fish is not male, he releases the fish into the tank and he tries again. He continues scooping until he finds a male goldfish because that's what the customer wants. So the first question is, what's the probability that it takes 5 trials to get a male? Well, we've done this before. We've been working on this in class, right? So in this case, what you have is you have a binomial distribution, right? So in order for the 5th trial to be a male, you would need to have the first 4 would have to be females. So you would get a female for the first one, you get a female for the second one, you get a female for the third one, you get a female for the fourth one, and then finally you get the male. On the 5th trial he gets the male. So the total probability, multiply all of those things together, and it winds up being 0.07203, and that equals the probability that x equals 5. Once again, you need to get in the habit of writing this symbology. Now, what if we change it a little bit? What is the probability, the distribution of x, the number of trials needed to find a male goldfish? So if we were going to make a distribution of this, we'd have our x variable, and we could have 1 trial, 2 trials, 3 trials, 4 trials, 5 trials, and so on. So we'll get to 1 trial, which would be a probability of 0.3 right off the bat. He gets it. Or you could have 2 trials, which would mean the first one was a female, but the second one you had success, so 0.21. Or you could do the 3rd trial, which would mean the first 2 were females, 0.7 times 0.7, but then the 3rd one was a male, so that's a 0.3. So that gives you a probability of 0.147. And you could keep doing this on and on and on and on for 4 trials, for 5 trials, and so on. And the question is, when do you stop? Could you just keep going forever? Because, I mean, that would take forever. But in this scenario, we don't know when to stop. We're going to stop when we get a male goldfish, but we don't know how long that's going to take. It could take 5 trials, it could take 1 trial, it could take 20 trials. We just don't know. So that's the distinction between this type of distribution and what we did before with binomials. Alright, so here's a couple of things you're going to want to write down about geometric distributions. So first, if the slide will ever move for us, a geometric distribution. We say that the random variable x has a geometric distribution if each of the observation falls into one of just 2 categories, either success or failure. This is exactly like binomials, right? Binomials have the exact same thing. They either succeed or they fail, no other options. Also for geometric distributions, the probability of success would be the same for each observation, right? It can't change from time to time. The observations have to be independent. One can't affect the other. And the 4th thing, and this is the one that's different between this and binomial, is that the variable of interest is the number of trials required to obtain the first success. How many times will it take to succeed? With a binomial, we knew it was 8 trials, 10 trials, whatever. For this case, we want to know we're going to keep doing these trials until we have a success, and at that point we're going to stop. That's the distinction. So for example, in our goldfish scenario, x equals 1, 2, 3, 4 goldfish, 5 goldfish. How far does this go? Well, the answer is it keeps going on to infinity. So if we're going to make a distribution, it's going to be difficult, right? So this is the distribution. This is the difference. The difference between binomial and geometric properties is that there's not a fixed number of trials in geometric distributions. Other differences. A binomial random variable will start with 0. Because you could have 0 successes, 1 success, 2 success, 3 success, and so on. A geometric random variable will start with 1, because you can't succeed in 0 tries. You have to at least try once in order to have a success, and that's one of the distinctions. Binomial distributions are finite, meaning they stop, while geometric ones are infinite, meaning they never stop. Here are some formulas that you're going to want to write down and you're going to want to make a note of. You don't have to memorize them because they will be provided for you on the test, just like they are on all my tests, but you do need to know what they are and how to use them. So the first probability is the probability that the first success occurs on the nth trial, or the xth trial. So if we want to know that probability, it would be the probability of success times the probability of not success to the x to the n minus 1, x minus 1. That is the formula for the mean, the average, the expected number of times you would have this happen. That would be the mean of x. The variance of x is given by this formula. And finally, the probability that it takes more than n trials to see the first success. So the probability that x is greater than 5 trials or whatever, and you would put that in there. Alright, so these are the 4 formulas you're going to need to know, and I'm going to give you some examples to use to go through them. And we will, of course, be talking about them in class, but you need to have them, you need to be able to refer back to them, you need to know what I'm talking about when I say the mean of x. Okay, so here's a couple of examples. We want to count the number of boys in a family of 4 children. Well, what are the values for these random variables if all we're doing is counting the number of boys? This is a binomial. We know there's 4 kids. There are no more than 4 kids, so therefore the random variable would be 0, 1, 2, 3, or 4. Either 0 boys, 1 boy, 2 boys, 3 boys, 4 boys, no more. Count the children until the first son is born. See the difference? In this case, it's geometric. Can't start with 0, but we start with 1. So 1 child until the first son, 2 children, 3 children, 4 children. Do they keep going until they have a son? That's the difference. Alright, there is a calculator command for geometric distributions, exactly like there is for binomial. It's located in the same place. So if you look on your graphing calculator, underneath that same distribution menu that we've been practicing with binomials, the geometric one is there as well. So the geometric PDF finds the geometric probability for p for the probability that x equals k. No n because there's no fixed number, right? In the binomial we needed a number. In the geometric we don't because there's no fixed number. All we need is the probability and how many do we want to have before we have our success. Geometric CDF, it finds the cumulative probability for x less than or equal to k. So the probability after 0, probability after 1, probability after 2, probability after 3, and it would add them all up. If we wanted to find the probability that it takes more than a certain number, we would do 1 minus the geometric CDF given up above. Right? And again, I'm going to give you examples of all of these, but you want to write them down so you can refer back to them. And when we get to the examples, hopefully that makes things clear. We're going to do some practice in class, but you should be asking questions. So now, what's the probability that the first son is the 4th child born? Right, here's how we set this up. Notice the notation once again. The probability at x equals 4, we want to write that probability statement, would equal the geometric PDF, because we want to know exactly the probability at 4. Probability of boy versus girl is 0.5. We want it 4, so we would use our formula there. What's the probability, second question, what's the probability that the first son is born at most after 4 children? That the first son is born after at most 4 children. So the probability that x is less than or equal to 4 is equal to the geometric CDF. Alright, so that at most it takes 4. We want to know the probability that for 0, for 1 kid, for 2 kids, 3 kids, at most 4. We want to stop at 4, but we want to add all the other ones up. And that's what a CDF does. Okay, here's another example. A real estate agent shows a house to prospective buyers. The probability the house will be sold to the person is 35%. What's the probability that the agent will sell the house to the 3rd person she shows it to? Right, so that is a geometric PDF, probability x equals 3, 35% success after 3, multiply it all out. How many prospective buyers does she expect to show the house to before someone buys the house? This is the mean. This is our expected value. We would do using the mean formula that I showed you earlier. 1 divided by 0.35 would equal 2.86 buyers. That's what she would expect. So back to our introduction problem, our intro problem. In a large fish tank, 30% of the goldfish are males. A customer desires a male goldfish. So the store employee scoops into the water and he captures 1 fish. What's the probability the pet store employee will need to scoop out 5 or more fish? So we want to know the probability that x is greater than or equal to 5. So using one of our formulas before, we know that's going to be 1 minus the geometric CDF, and there's a 30% success rate, so 0.3 comma of 4. Alright, so we want to take the probability of 0, 1, 2, 3, and 4, add them all together. That's what the geometric CDF does. And then do 1 minus that, because if we are accounting for 0, 1, 2, 3, 4, then 1 minus that would be 5, 6, 7, 8 on to infinity. So using your calculator, if you multiply all that out, you should get the answer, which is 0.2401. And that then would be the answer to that question. Okay, so that's the end of the slideshow. Hopefully you have all your notes and you'll come to class ready to go tomorrow. Thank you, and I hope you have a good rest of the evening.